Welcome to This Explainer. Today, we're going to build your ultimate scientific toolkit, step by step, and I am so excited to guide you through this material. Whether you're stepping into a chemistry lab for the absolute first time, or you're just trying to understand the hidden science in your everyday life, having the right foundational skills is absolutely crucial. Today, we aren't just going to memorize facts. Instead, we're going to learn how to see the world exactly the way a scientist does, through precision, organization, and clear analysis. Here is our roadmap for today. First, we'll cover why accurate measurements matter. Then, we'll look at the 5 physical quantities, using tools and avoiding errors, and organizing your scientific data. Finally, we'll wrap up by understanding solutes and solvents, followed by a quick recap of your science toolkit. Let's dive right in.
Part 1. Why accurate measurements matter.
As you can see, illustrated here, standards set by educational bodies are super important because they ensure we're all speaking the exact same scientific language. Think about it. If a researcher in the Philippines discovers an amazing new chemical reaction, a scientist in Brazil or Japan needs to be able to replicate it perfectly. To do that, they can't just rely on vague descriptions. They need absolute, standardized measurements. Science is a massive global collaboration, and accurate measurement is literally the universal language that makes the whole shebang possible.
So the crucial question we have to ask ourselves is this: why do scientists bother measuring things so meticulously instead of just relying on a really good guess? Imagine an engineer just kind of eyeballing the length of a bridge cable, or a doctor estimating a dose of medicine based on a quick glance. I mean, it sounds absurd, right? Guessing leads to errors, unreliable data, and totally failed experiments. Measuring, on the other hand, gives us objective truth. It removes our human bias and provides us with solid facts that we can test, verify, and actually build upon.
Moving right along to Part 2, the 5 physical quantities.
Basically, physical quantities are just the measurable properties we observe in any given object or system. Standardizing them is the key to making sure our data is valid anywhere in the world. We standardize these using what we call SI units, which stands for the International System of Units. This system is adopted globally to prevent the absolute chaos that would happen if everyone just decided to use their own personal measuring system. Take a look at these core 5 essential quantities we measure daily, alongside their globally accepted standard international units. We've got length measured in meters, which tells us how long something is. Mass measured in kilograms, telling us how much matter is packed into an object. Volume in liters, showing how much space a substance takes up. Time in seconds, tracking how long an event takes. And finally, temperature, measured in Celsius or Kelvin, indicating how hot or cold something is. These 5 right here are the absolute pillars of your scientific toolkit. To put this into plain language, checking how tall a sunflower grows, looking at that distance from the roots to the petals, that is calculating length. Meanwhile, finding out how heavy a bag of rice is gives us its mass, because we're quantifying the actual amount of matter packed inside that bag. Visualizing real-world examples just like these makes those abstract quantities immediately relatable.
Now, it does make you wonder, if scientists internationally used SI units like meters and kilograms, why do we still use English units like feet and inches in our everyday personal lives? Well, honestly, the simple answer is tradition and habit. For casual, everyday tasks, familiar units are just passed down through generations and local cultures. But the second you step into a laboratory or need to share data internationally, you've got to switch to those SI units to ensure absolute precision.
All right, let's look at Part 3, using tools and avoiding errors.
Now, a really vital concept to grasp here is called the least count. This is literally the absolute smallest value your specific tool, like say a graduated cylinder, can read accurately. So you've got a ruler, right? And the absolute smallest little lines on it are millimeters. That means the least count of that ruler is exactly 1 millimeter. You can't accurately measure half a millimeter with it, you'd just be guessing. Understanding the least count of your tool tells you exactly how precise your data can actually be.
If you want to gather truly reliable data, you've got to follow a strict methodical workflow. Step 1, use the tool correctly, making sure you always start at the true zero mark. Step 2 is incredibly important. You must read the measurement perfectly at eye level. If you look down at a liquid in a cylinder from above or maybe up from below, the reading is actually going to look slightly shifted. We call that parallax error. And finally, step 3, always record the number right alongside its correct unit. A number without a unit is pretty much meaningless in science.
You'd be surprised how often simple mistakes ruin a good scientific investigation. Guessing a value that falls somewhere between the lines of your tool's least count or reading a measurement at a weird angle are huge offenders. Another major pitfall is writing down the wrong unit. I mean, imagine recording a tiny plant's growth as 10 meters instead of 10 millimeters. Being aware of these common errors is your absolute best defense against making them.
Section 4. Organizing your scientific data.
Once you have your accurate measurements, you need to organize them. Take a look at this elegantly structured table. It shows exactly how you take raw data, like measuring coins, and organize it into clean columns and rows. Notice how the first column clearly identifies the object, coin 1, coin 2. The next columns have specific headings, with the physical quantity and the unit right there in parentheses. Circumference in centimeters, diameter in centimeters. Structuring it this way lets us instantly compare the data and hunt for patterns, which is the very essence of scientific discovery.
Moving to Part 5, Understanding Solutes and Solvents.
Let's apply all this to a real-world chemistry concept. Every single solution has two main parts. Look at this clear comparison. The solute is always the substance present in a smaller quantity. It's the thing that gets dissolved. The solvent, on the other hand, is the substance present in a larger amount that actually does the dissolving. If you can just remember this simple relationship, smaller gets dissolved, larger does the dissolving, you have officially mastered the basics of solution chemistry.
Let's test this out with a practical scenario. What exactly happens when you mix juice powder into a glass of water? Think about the quantities for a second. You usually have a small scoop of powder and a nice big glass of liquid. Applying those definitions we just talked about, we can easily predict how these two components are going to interact.
Well, in this case, the juice powder is the smaller amount, so it acts as our solute. It dissolves seamlessly into the water, which, being the much larger amount, is our solvent. Together, they create a complete, uniform mixture that we call a solution. The solid solute might seem to disappear, but we know it hasn't. It's just perfectly distributed throughout the liquid solvent.
Okay, let's do a quick knowledge check to consolidate what we've learned. Looking at these four options, cooked flour, marshmallow, seawater, and blood, which one of these represents a perfect, natural solution, where a smaller solute is completely dissolved in a larger solvent? Take a second to think it through.
If you guessed C, seawater, you hit the nail on the head. Excellent job applying what we've just learned. In seawater, solid salts, which are your solutes, are completely and evenly dissolved into the vast amount of liquid water, which acts as the solvent. It is literally a massive, naturally occurring chemical solution that covers most of our planet.
And finally, Part 6, a quick recap of your science toolkit.
Let's do a really quick rundown of the main takeaways we've built into your toolkit today. From utilizing standard SI units so your work is globally understood, to finding the least count of your instruments so you're never guessing, you now know how to gather precise data. Plus, you know how to organize that raw data into clean tables, and you can confidently identify the solutes and solvents that make up solutions. Honestly, you are officially ready to step into a lab and conduct some rigorous experiments.
And that brings us to a final thought for you to chew on. Tomorrow, when you're measuring an ingredient for a recipe or simply stirring sugar into your morning coffee, how will you see the hidden science right in front of you? Will you think about the mass, the volume, or maybe that exact interaction between the solute and the solvent? You see, science isn't just something that's confined to a classroom. It's the fundamental rulebook of the universe playing out in your own kitchen every single day. Stay curious out there, keep measuring, and I'll catch you in the next explainer.